I am the nature hacker, and this is your world. So today I want to talk about physics risen from the dark ages. So if we look into electrical engineering, chemical engineering, we notice many laws dictating things. And in electricity we have resistance, we have voltage, we have current. But we don't have the concepts of resistance in mechanical engineering. Also, there's another principle of directionality. I'm not quite sure if directionality has been defined in electrical engineering or chemical engineering, but in mechanical engineering, directionality hasn't been defined. So in my fourth and fifth laws of Newtonian type physics, down in the description below I have links to my fourth and fifth laws, and what they describe, the fourth law describes something that I'm going to term directionality. It's how directional a fluid transfers forces. Okay, and some people say, oh, forces can't be transferred. Well, what I mean by transferring a force means how much the force that one body is undergoing, how much of that force can also be applied to another body. Okay, and I define that in terms of how much interaction the two bodies have together. So if there's no interaction, if there's zero interaction, the only force that will be applied is a perpendicular force. You know, this body will contact another body, and the only force that can be applied from this body to this body is the perpendicular component. So that's if there's no interaction between the two bodies. There is transmitted a perpendicular force. Okay, and obviously, if there's you know, if the angle goes down to zero, there's no force applied, right? If the movement is parallel to one another, there's no force applied. If there's 100% interaction between the two bodies, then you get the whole force transfers. Even if it's moving parallel, if the interaction between the body and the body is 100% interaction, it will move it. It's like static friction, basically. It will move it. It'll apply a force in that direction. You know, and so any angle, it will transmit all of its force to the other body if there's a full interaction. So that is termed directionality. How much of the force can be transmitted given the angle, given given the interaction between the two, and that's pretty much it. So that's the directionality of your material. Now let's say you want to absorb a bullet impact. Do you want highly directional transfer? No, you do not. Because a highly directional transfer means that bullet's force is transmitted directly back to you, right? But we don't want that to happen. So we want a material with low directionality. That means that it does not transmit forces directly behind it. That means that it only transmits perpendicular forces. So this force, you know, gets broken into these forces, and then those forces get broken into two more forces, etc., etc. So you're spreading out that force. Okay, that's what you want to do for bulletproof materials. And that's what non-Newtonian fluids are. They're very non-directional in some ways. So, and see, now that's not only all. I mean, that's the most basic physical representation I could conjure up, okay? But there needs to be a more full understanding to define liquids and gases. So in order to transmit a force, you need to have these types of interactions. And if the interactions aren't forced, if you're not forcing the interactions, and you have unconstrained degrees of freedom, like let's say you're pushing against a liquid, right? Instead of the liquid just, you have a blob of water, right? You have a blob of water. If you push that water, is it just going to stay in a blob and go forward? No, it's going to spread out on your hand, and it's going to flow off of your hand, right? And some of the water is going to come up over your hand and stay where it is and not get pushed, right? So what you need to do is you need to constrain that water in a 3D shape that constrains 2 degrees of freedom. It constrains this degree of freedom and, 2 dimensions. You got this and then this. This dimension, let's call that the x-axis, and then the y-axis here. So you're constraining that liquid in the x and y dimension. And for gases, in order to be able to transmit a force to them, you have to constrain their 3 degrees of freedom, okay? And their 3 degrees of freedom are the y-axis, the x-axis, and the z-axis. Because if a gas is not confined in the z-axis, it can escape out the opening. So that is what has to happen for force transfer. And I know that the liquids and the gases haven't really been defined by equations yet, but I think we can use iterations of that original equation I described, the force transfer equation of bodies. I think we can use iterations of that equation to apply to things with 2 degrees of freedom like liquids and things with 3 degrees of freedom like gases. We're just going to have to apply that equation more times, kind of iterate it, if that makes sense. And I don't know, if you have a proposal on how to make an equation for a liquid or a gas, I would love to hear it. Let's get this done. If you get an equation done, I mean, you will get credit for developing that equation, so please work on it. Alright, and now the second aspect is something I'm calling resistance. This is mechanical resistance. It's analogous to electrical resistance, alright? This can also be called momentum transfer, force series, things like that. But what it is it's the resistance. So notice in electrical engineering you have V equals IR. You have R is equal to V over I. V is like potential energy, right? I is current. Now, in mechanics, we have similar things. The potential energy in mechanics is momentum, okay? So we have our mechanical resistance, and that's equal to momentum over force. So force is analogous to current in an electrical system. So you have mechanical resistance is equal to momentum over force. So the higher the resistance is, the higher the voltage that you achieve is, which is the higher the momentum you achieve is. So the higher the resistance, the more momentum you can create from a given force. Okay, does that make sense? You can replay that over again if you wish. So I feel like these equations are really relating. They're really bringing mechanical engineering into out of the dark ages, right? I mean, because we only had 3 laws before, and they kind of sucked at defining how things work in the real world. So these 2 new laws can really help us to bring Newtonian physics to the next level and to really use mechanics and motion to do things that we've never been able to do before. So yeah, so this is defining non-Newtonian physics in Newtonian terms. So please work on these equations. Please follow the links below and think about these laws and see if you can improve them, or you can find bugs, or you can create equations. I mean, anything you do will be recorded, and you'll get credit for that, So please do so. Thanks for watching. I am the Nature Hacker. Do work.